Hi guys, welcome back to Confusing Bits. I am Corey, and I'm here to talk to you about Lost in Math by Sabine Hossenfelder. So this is a book, as you can see on the title, it says How Beauty Leads Physics Astray. This book is about how basically the last 50 years of physics has been kind of gone off the rails as far as usefulness goes, as far as scientific rigor, I guess you would say. The Too Long Didn't Watch, Too Long Didn't Read it's a great book, especially if you're interested in science. You don't necessarily have to know a whole lot about physics or science in particular, but it does talk about the scientific method. It talks a little bit about some of the topics that modern day physics is exploring. You don't really, she introduces all of these topics as she goes, but and explains why they're important for the most part. But the more is to the point about why the things that we're doing in the physics world, why the things that physicists are doing, or maybe not the best approach. So yeah, it's a good book if you're scientifically curious or whatever. This is definitely a nice book into the actual realism of day-to-day science. Yeah, that's the heads up in book. Let's do the spiel, right? For more than 100 years, physicists have taken John Keats' admonition that beauty is truth as nearly gospel. Whether they are pondering the existence of black holes or predicting new discoveries at CERN, physicists believe that the best theories are beautiful, natural, and elegant. This standard separates popular theories from disposable ones. Unfortunately, as physicist Sabine Hossenfelder argues, this standard is also why we haven't seen a major theoretical breakthrough in physics in more than 4 decades. In Lost in Math, Hossenfelder explores how this modern preoccupation with beauty blinds us from seeing the natural world as it really is. Led by their aesthetic criteria, physicists have concocted mind-boggling new theories, invented dozens of new particles, and declared that distant places across space are connected by wormholes. But observation has been unable to confirm almost all of these ideas. In fact, many of them are actually untestable. In spite of these contradictions, theoreticians are convinced that their graceful equations and elegant formulas contain higher truths about nature, and that these too good not to be true theories have left the field stuck in a cul-de-sac. To break out of this rut, physicists must rethink their way they construct their theories. Lost in Math reminds us that not only that only by embracing messiness and complexity can scientists discover the truth of our universe. Sabine Hossenfelder is a research fellow at Frankfurt Institute for Advanced Studies and author of the popular physics blog Back Reactions. He has written for New Scientist, Scientific America, and Nova. She lives in Heidelberg, Germany. She also has a fantastic YouTube channel. If you would like a nice, no-nonsense, and this is why I watch her, a nice no-nonsense YouTube channel that's not just rah-rah cheerleading science. It's not like negative or anything, but she does a weekly news show where she talks about all of the scientific news from last week, and occasionally she'll have other videos where she talks about some like the journalists are going crazy about some new paper or something or other, and of course they're getting it wrong like they always do, and so she talks about, she kind of like tamps down on some of the heights. It's not a negative channel. I'm trying to say this. It sounds like I'm saying it's a negative channel. It's not. It's a really great, but it's an even keeled look at science, because I don't know what has happened. Like, is when maybe it was from my generation. Maybe my generation is to blame. But when I was growing up, science was something that pretty much only nerds did, right? And at some point, science turned into this rah cheerleading thing, where go science, and science is the best tool, and yay, math is awesome. And I mean, it is all of those things, but at the same time, probably to state another controversial term is like trust the science, right? That kind of got into the conscience of like follow the science, trust the scientist. Kind of got into the public conscious or whatever, and that's completely wrong. That's not what science is. Science is not a bunch of facts. It's a process, and it's a messy process. It's run by humans, and we get things all wrong. And that's the whole point of science, is to correct that wrongness. And it happens over long time scales. It's messy. We get it wrong. The things that we guarantee, that the things that we think we know right now, and not in and I don't mean trivial things. I mean, there are big concepts that we think we know right now that are going to be proven wrong because it's happened in the past over and over and over again. Like lobotomies used to be amazing, but now we're like, oh, there's a horror, right? You start thinking of somebody getting a lobotomy. That's horrific, right? But that was high science back in the day, right? And it's not just limited to although it is very prevalent in the human-based sciences, because they have trouble. I'm always, if you've been following me for a while, you know I will rag all day long about anytime a science has to touch human behavior, economics, philosophy, psychology, nutrition, medicine. Anytime you're dealing with humans, you basically almost throw out the scientific method. You're not going to get any real experiments done. And you're going to get the science wrong. That's why nutrition always says one day cholesterol is the devil, and the next day it's perfectly fine, and then one day it's saturated fat, and then the next day it's salt, and then one day it's this antioxidants, and then the next day it's not just the journalists screwing overblowing everything, although that is a big part of it. That is a huge part of it, is the way science is reported on. It's also the science itself is based off of this observational data that isn't actual experiment, and you can't prove causation without experiment. Not generally speaking, you cannot prove causation without an actual experiment. You got to do the experiment. You got to do a controlled experiment, and most of the time, it's either too much money or just impractical in some way, or just straight up impossible. Like how are you gonna do some types of experiments on diet in human whenever we can taste the difference between food? It can't be, the observers may be able to just by taste be able to tell the difference between two different foods, and that can influence the experiment, right? So I'm always ragging, if you can't tell. I'm always ragging on science that has to do predominantly with observational data. And a little bit more controversially, I don't know if you noticed, like astrophysics is almost all observational data. Now, thankfully, they usually still have to report to the rest of their physics colleagues, so they're going to get their theories shot down pretty quickly, because it's a very grounded science there. But if you really start, that's why, like, we will never know if there was we will never know if the Big Bang happened, right? We could say all signs point to yes, but we can never do that experiment, right? We can't say, okay, let's create our own, and so we can create our own. There's no experiment where we could prove that the Big Bang happened, right? That's just how the math tells us. We don't know it actually happened back then, because there is no history, we can't run an experiment. We can't observe that past directly, so we will never know. But that's just that's the limitation of the science. But you'll take it as a given. People will take it as a given that the Big Bang happened, which it probably did, maybe not. Who knows? We don't really know. What happens in a black hole? We don't know. We can't observe what happens in a black hole. We can only guess from the mathematics that we do know, because nothing comes out. We can't observe anything coming out of a black hole, so we'll never know what happens in the middle of a black hole. It's little things like that, right? Climate science. We can't run an experiment on another Earth to confirm that our models, we have mathematical models that run on these huge supercomputers that model the atmosphere, and then we think that based on all of these criteria that whatever, the temperature is going to raise by 2 degrees. Maybe it is, maybe it is. I'm not saying it is or not. But the thing is, we can't run the experiment that will prove the validity of that model. We have to, it's guesswork. Like, if it gets it wrong, we go, let's say it's going to be, in 50 years, the planet's going to be 2 degrees hotter. Well, we can't do the experiment that will confirm this model versus this other model that predicted a 3-degree difference, right? We can't do that experiment. So it's all observational, right? I mean, we can collect a lot of data. We can look at the physics and stuff like that. But we're talking about hugely complicated systems here. We can't really say that this model is the correct one, or at least is more correct than this other one, on any useful time scale. Is all I'm saying. That's why if you go back in time and look at quite a few of these predictions, you're going to see a lot of variance between the different predictions. There's not just. They will say all climate scientists agree. Well, which particular model are they agreeing on? I'm not saying that that climate change is not happening. I'm not saying that the world that things are not getting hotter. I am not saying that. I'm saying that we can't verify any of these scientists' predictions until we're long dead. So that's all I'm saying. All signs point to yes, that something's going on, and it's going to be in this order of magnitude of this change, and then these are the kind of things these are the first order effects that probably will fix the situation, but we won't really know. We're guessing, and we need to be very clear about when we're guessing and when we do know, so anyway, that's a big part about what the science is. So my training was in physics, in experimental science. So I studied physics. I never graduated, but I studied physics, and I did research science in a chemistry lab. We were doing this is just for context. My scientific background is I did some science in the realm of nanotechnology. We did chemistry, so I was a physicist working in chemistry, analytical chemistry, specifically talking about metallofluidics. So I have some measure of professional scientific experiment. I know how science actually works far more than maybe the layperson has with science. I don't have this romantic. I don't have only the romantic notions about science. I know how things kind of work on the ground day to day, to some extent, far more than most people. Let's say, wouldn't call myself an expert, but I have more than I have professional experience. Let's put it that way. We'll just leave it at that. So my training was in physics. And so that's what got me into here, because I used to get all of these books. There was all of these. Where's it? I got them right. All of these types of books. The Elegant Universe and Brian Greene. There's going to be a bunch of Brian Greene books. Brian Greene's The Fabric of the Cosmos and John Gribben, The Search for Supersymmetry and Symmetry. All of these are like physics books, right? But most of them are like popular science physics, where they talk and flowery language about the beauty of physics and the mathematics and stuff. And this is what got me into physics, right? So I'm not knocking it in one way, but in another way, it's also it also gets things very wrong in the same way that they're talking about in this book, and that is focusing on the beauty of physics has gotten the field practically nowhere. Especially in particle physics, practically nowhere, no major discoveries in my lifetime. We haven't had a major discovery. You may be thinking, okay, well, what about the Higgs, right? They predicted the Higgs was discovered by CERN, like, what was it, 5-10 years ago or something like that? The Higgs, that's relatively recent. No, that was predicted like in the 60s, 50s or 60s or something like that. That's how old that. We just took a while to confirm it, and we had a lot of very grounded. And she talks about it. We had a lot of very grounded reasons about why we should expect the Higgs to be, and we knew where it was going to be, generally speaking. So it wasn't really a surprise. It was kind of we kind of expected it to happen once we got the CERN got things up and running. The LHC was at the right power level. We knew we should expect to find the Higgs, and indeed that is what we found. But what she talks about in the book, and also what I have been reading about, all of these supersymmetric particles and massive particles and all of this stuff that we expected to find from these experiments, they were all predicted off of beautiful mathematics. Basically, a lot of notions of symmetry, which I'll be honest, I don't even understand all of the symmetry arguments and stuff that they're talking about, but there were notions of mathematical symmetry that cause, okay, well, if we have this particle, then this other particle must exist because, you got to need the yin and yang, just to put it in everyday parlance. There was some sort of, there needed to be a symmetrical partner to match all of the particles that we do know, and then we expected them to have this amount of energy or whatever, and so, but none of that was played out as we they were predicted to show up at certain energies. We would find certain particles. We expected that were predicted, particularly by like string theory and stuff. I know if you've ever heard anything about physics, you talk strings underlie the universe, and they're tightly bundled up, and they spread throughout the cosmos, and they form all the space and time, and ooh ah wah, and you got the symphonic music playing in the background as the speaker talks with the baritone voice, just entrancing you about the mathematics and the beauty of physics, and you're just completely enchanted, and but it's all bullshit, because when we do the test at LHC, we go ever higher and higher energies. We're just marking out all of these energies where these particles don't exist. We look for them, we didn't find them, and so the realm of possibility just keeps getting higher and higher. Well, and so we'll move up. So if it doesn't show up here, well, okay, well, we just need a bigger collider. We just need to spend $1 trillion on a new particle, an even bigger particle collider, so we could finally see these supersymmetric particles, these super heavy, massive particles. There are decades-long experiments that are like in the bottom of these deep mines, and will have these big old huge water tanks, basically, with little light detectors in there, and what they're looking for is these super heavy, massive particles that come flying through, and they interact really weakly, but they're super massive, and they'll come through this water, and occasionally they'll spark a light in this particular way, and we can catch it in the detectors. These experiments, multiple different experiments and multiple different variations, have been looking for these supermassive particles for decades. Still hadn't found a damn thing. Like, we're talking billions of dollars down the drain looking for particles that were only predicted based off of mathematical beauty. In large part were predicted, or a large part of their argument, if there was any other argument at all, was predicted off of just the beauty of the mathematics that explained that they should exist. As I understand it. Again, we're talking about theoretical physics here, so talking about it in a grounded way is beyond my capability. It's probably beyond your capability to understand it anyway. So anyway, so we have all these theories that predict all of this behavior here. We have all those experiments. We're spending all this money. And the thing is, when you go back and look, and this is the point of the book, if you step back and look, there was actually never any onus from the get-go to come up with this other reformulation of this theory. It was based purely off of aesthetics. There was no reason, there was no inciting data or whatever that says that there's a problem with our current theory. There's something that our current theory predicts, and it gets wrong because we have this experimental evidence that says, okay, there's something wrong, verifiably wrong with our current everyday model, which is called the standard model. There's something wrong with our model. As we understand the standard model, it predicts one thing, experiment bears out a separate thing. There's a problem with our model because the arbitrator is the experiment. The experiment says we're wrong. The thing is, there isn't. Standard model, there's no prediction that the standard model makes that proven otherwise by experiment. That's the problem with physics, is that we got it right. And we've spent the last 4 or 5 decades coming up with more and more. Of course, there are problems. There are things that we would like our model to explain. There are questions that we have that our model doesn't explain. But our model is not wrong according to all of our understanding. As best as we understand, for the most part, our model doesn't have any particular flaws that demonstrate a need for a new model. And so that's the thing. That's one of the key points that Sabine talks about in her book, is that we've gotten off the rails. We've lost the plot. Physics, by we, or I'm talking about physicists or whatever, or mankind in general, via the physicists, have lost the plot. They don't have a reason to come up with these new theories, but they come up with them anyway because they think they're beautiful in some aesthetic way. And you could look at one physicist will look at one theory and say that's beautiful, and another one might say that it's not. So it's completely arbitrary about what is considered beautiful, because obviously beauty is in the eye of the beholder, right? So we don't have a reason, a really driving reason that to make us think that our current model is incorrect. There are things that we would like our model to be able to model. So there's 2 big theories in physics. There's what's called the standard model. And standard model is all of the particle physics stuff. It's electrons, protons, neutrons, and photons, and neutrinos, and tau neutrinos, and quarks, and gluons, and all the particle physics stuff. And so that's all like quantum field theory stuff. This is all this stuff is based off of quantum field theory, basically. And then on the other hand, you have Einstein stuff, which is general relativity. That's so all the standard model stuff is basically all small scale stuff. This is stuff that you test mostly in particle colliders, or maybe these detectors. I talk about these scintillating detectors that are like big tanks of water in the middle of the ground. That's particle detection. That's small scale stuff And then on the other end, you have Einstein. So Standard Model was like a whole bunch of people contribute to this. Even Einstein contributed some parts of the Standard Model. But Einstein almost wholly created what we call general relativity, right? That's what he's most famous for, was special relativity and then general relativity. But that's large stuff. That's universe. That's like solar system scale. That's heavenly bodies moving around. That's the curvature of space. That's gravity. That's just almost completely gravity, right? Light interacts with gravity and causes the wavelength of the light to shift. That's where you get the red shift and the blue shift, and that's how you get time dilation and all of that stuff. But that's huge scale gravity stuff. And the thing is you're not going to be able to detect gravity stuff inside of a particle collider because the scales are so widely off. You need the scales of the heavenly bodies, right? You need the scales of Earth, the moon, the sun, or at least very large asteroids before you can really start talking meaningfully about gravity. And you're just not going to see those types of effects inside of a particle collider. And they are mathematically speaking, they are very different. Relativity is based off of the curvature of space-time fundamentally. You can think of it that way. It's based off the curvature of space-time, and the Standard Model is based off of quantum field theory. They're just not compatible. You can't just like easily glue them together into one coherent whole. And that's the theory of everything. If you've been following physics or the science cheerleading like I have, all of these books are talking about, most of them are talking about a theory of everything. They're talking about M theory, string theory, gauge theory, whatever, all of these different theories that try to unify all of the known forces into a single model. But we don't have that. We have the Standard Model, which is the strong, weak, and electromagnetic force, and that's the Standard Model. And then you have gravity. It's the four forces, right? But we can't glue them together into one. Relativity is the gravity, right? We can't glue them all together, and that's what we want. We want that unified theory, but it's not forthcoming. The way they're formulated mathematically, there's not a clean way we don't know how to do that in a way that is testable. String theory, they thought could do it, right? Well, there's been several different types of theories that they thought could unify these models together. One of the most popular ones has been the thing called string theory, but string theory is literally a million different theories. It's a whole class of theories. But string theory, and if this one's wrong, then you reformulate it slightly and you get a completely different theory. That's part of the problem with string theory, is you can never falsify it, because you prove this one wrong, but there's other slightly variation. You just treat the parameters. Oh, well, it's actually it's obviously not that one because it's wrong. So we'll just do this other one. And obviously, if you build this $400 billion detector, obviously we'll find the predictive properties of this particular formulation of string theory. It's the slippery slope. Like the finish line keeps getting moved with string theory, which is why anybody from the outside looking at it go, okay, this is bullshit, right? But that's the problem, right? So that's what this book is about. And much better, more eloquently stated version, it talks about how we actually have no reason. We don't. There are some questions, and that's another the big part of the book, is it talks about all of this focus on trying to find the theory of everything is actually making us not focus on questions that we can actually make some traction on if people, if the theoreticians actually spend some time on these questions. She talks about, I'm not going to pretend like I understand what she knows, she talked about the measurement problem in quantum physics. I don't know if you ever heard of Schrodinger's cat. It's related to that, where like what does a measurement actually mean in quantum physics? There's not really a very clear definition. So I imagine that's what she's talking about as far as the measurement problem with quantum mechanics is what are the criteria for what criteria qualifies as a measurement, and what are the primers, so that's one question. She talks about a couple other ones that we could be making progress on, that seem tractable, but we don't, because all our best minds are, if they're not quants on Wall Street, if they hadn't gotten if our best and brightest theoretical physicists were not working on Wall Street, if they're still in academia and they were still working on theoretical physics, if they weren't focused on string theory or on Wall Street, then they would maybe actually spend some time on these other problems that probably are solvable, right? And we could make headway towards some actual new physics. Maybe not the fancy new unified theory physics, but enough to actually move the needle, right? I'll give you an example. I know this video has gone on long enough about how how quantum field theory or quantum mechanics was discovered in part. How we knew that we needed a new theory, and then we ended up discovering quantum mechanics. There was the thing called the ultraviolet catastrophe. So back in classical physics was like Newton's physics, right? It was calculus, and you had continuous values and all of this. It was continuous values and integration and stuff like that, and summations. It was if you've done classical physics, like your physics 101 stuff, that was all classical physics, right? A equals ma equals F equals ma, that kind of stuff. That's all classical physics. There was a problem that all our theories of, I'm going to butcher this because this is messing, this is dragging up the cobwebs. There was a problem with our theory of light. It was called black body radiation. So you would take like an iron, right, and you put it in the oven and you heat it up. Right? So you put the iron in the oven, you heat it up, and it would start to grow. First, it would glow. It would grow like a dull orange, right? And then it would grow. It would glow red, and then it would grow orange, and then we would start getting white hot, right? And as you got hotter and hotter, it got brighter and brighter, and it was predicted that it should eventually, the light produced by that black body, the iron or whatever, that if you got it hot enough, it should produce ultraviolet radiation. The thing is, that didn't happen. It would level off, and you would get nothing but you would get a different light frequencies would be we predicted a certain range we predicted ultraviolet light frequencies. We didn't get those ultraviolet light. There was a whole, we had our formulation, we had our theory about what should happen, and it was disproven by observation. So we knew there was a problem with our model, and that problem turned out to be fixed by what ended up being called quantum mechanics. That there were specific orbitals inside of an atom, and as the electrons jumped the orbital, they would release photons of a specific wavelength. They were quantized, only that they could only move at specific jumps between the different orbitals depending on the type of atom, and that's why you couldn't get the ultraviolet rays in actual observation, because there was no orbital jump. There was no orbital jump that corresponded to those ultraviolet frequencies. It was quantized. And that was the beginning of the end for classical mechanics. Is we moved. You could use everyday Newton's classical mechanics works for everyday stuff, but once you start getting into particles and stuff, you start needing to get things quantized, and that was the first big. It was called the ultraviolet catastrophe. We knew that there was something wrong with our model, and a new model that was predicted. New model that was formulated predicted that quality, predicted that behavior along with all the classical behaviors. It was subsumed altogether into quantum mechanics or quantum field theory. Eventually, that's what it was called. And point is, we had a theory, and we had observations that didn't agree with the theory, so we changed the theory, right? That's how science works. It's messy, but we had a prediction, it was proven wrong, and we changed the model. We didn't change the model just willy-nilly. We didn't say, okay, well, I don't like that this model has 2 parameters. It needs to have 3 parameters for some aesthetic reason. Well, let's just introduce it for any, just for pure vanity, That's kind of the point that she was making. She didn't make that point in the book, I don't think, the ultraviolet catastrophe. But there's several differences. You have some model that we're using as part of the science, and then we see some observations that don't agree with that model. Well, that tells you that there's new physics that's not enclosed in this model, so you change the model then. That's not the case now. Nowadays, everything that we can calculate, now that's a different problem, is being able to calculate things with the standard model. But everything that we can calculate with standard model agrees with what we have observed, right? There may be things that we observe that we can't calculate with our model, just because the math is too hard, right? But that's a mathematics problem. That's not a problem with the physics, right? That's not a problem with the physical model. It's a problem with just the mathematics, the logistics of the mathematics, right? So anyway, geez Louise, this 40-minute video talking about. Well, of course it's about physics. We're going to ramble on. Anyway, I hope you guys found it useful. I definitely read this book. It's really great if you're scientifically curious or whatever. It's a very kind of sobering look. That's kind of in contrast to a lot of the rah science hoopla that's out there. It's not a negative book. It's in fact, it's talking about something very important. It's talking about that there's hope in these other things. We just pay attention to them. Anyway, that's all I got. I definitely recommend the book. It's Lost in Math by Sabine Hossenfelder, and I hope I got her name right. As for next week, I got to do this book. It should tell you what's coming. We're going to do the first book in the Wheel of Time series, The Eye of the World by Robert Jordan. Yeah, book 1 of the Wheel of Time. Yeah, this one's going to be fun. I still got ways to go too. Jeez, I'm only halfway through my books. All right, yeah. So I will see you guys then. Toodaloo.